Hello, everyone. I'm Shruthi. I'm a graduate student at IISc Bangalore. I'm going to talk about the problem of underranking in group fair ranking. This is a joint work with Amit Deshpande from MSR and Anand Lewis from IISc. This work appeared in ICML 2021. So here we consider the problem of ranking defined as follows. Given a set of n items, we want to rank them in the order of their merit. For example, in search engines, the documents are ranked in the order of their relevance to the user's query. So here relevance could be considered as a measure of merit of the document. Whereas in the job interviews, candidates that are in the application process are first ranked according to their performance or previous academic record. This could be considered as a measure of merit. For example, consider this ranking on the RHS. So here there are 6 candidates that are being ranked. Usually the convention is that the item ranked in the first rank has the highest visibility, and the visibility decreases as we go to higher rankings, higher ranks in the ranking. And also notice that the candidates that are being ranked could be partitioned based on certain demographic features such as age, gender, race, etc. For example, here the candidates in ranks 1, 5, and 6 belong to the group female, and the candidates in the ranks 2, 3, and 4 belong to the group male. So now, when some of the items belong to a group that has been historically marginalized due to some human biases or historic biases, then is this merit-based ranking truly fair to all the groups of items in the data? So one issue with directly ranking people, the candidates based on the merit, is that an item's observed merit could be biased. This could be due to historic or human biases. It need not be a true indicator of a candidate's potential. And even if we have some fairness constraints, some badly specified fairness constraints for ranking may not give us a fair ranking. For example, if we say the top 6 ranks, there needs to be at least half female candidates. All the female candidates may be ranked in the bottom of the ranking, so that fairness constraint is satisfied, but it still may not be considered fair to the candidates in the female group. So one way to fix this is to define group fairness constraints in every prefix of the ranks. So a ranking is set to satisfy group fairness in every prefix of K. If for every K prime less than or equal to K, the top K prime ranks have at most certain upper bound and at least certain lower bound on the number of items from group L. So these upper and lower bounds are the group specific. Let's say the lower bound on the female group for a prefix of length 4 is 2. Then clearly this ranking that doesn't satisfy that constraint. So various previous works have studied group fairness and ranking algorithms. So they can be broadly categorized into 2 different types of algorithms. So the first one being re-ranking algorithms, where given a true ranking, the algorithms output a rearrangement of the items such that after rearranging the items, the ranking satisfies group fairness. So the other type of algorithms are the learning to rank algorithms, where we are just given some features of the items, and the learning to rank algorithms directly learn a merit score of the item, such that if we simply rank the items based on the decreasing order of merit, then that itself satisfies all the group fairness constraints. So in this work, we focus on the re-ranking algorithms. So we consider a slightly different notion of group fairness as opposed to the group fairness in prefixes. we first define group fairness in consecutive ranks. So here, every k consecutive ranks means that in ranks 1 to k, 2 to k plus 1, 3 to k plus 2, and so on. In these k consecutive ranks, the ranking needs to satisfy some lower and upper bounds on the number of ranks assigned to a group L for every group. Consider this other notion of group fairness in blocks, where we want the ranking to satisfy lower and upper bounds of the groups, representation of the groups, only in blocks of size k, that is ranks 1 to k, k plus 1 to 2k, and so on. Clearly, group fairness in blocks is much weaker notion than the group fairness in consecutive ranks. So you can think of this as a scrolling, as you're scrolling through a search result where at a time you see a window of size k, then we want that window to be group fair. So that is captured by these notions of group fairness in ranking. Okay, so let's look at this example where there are 6 candidates. Again, every 2 consecutive ranks should have at least 1 female and at most 2 female candidates. Similarly, every 2 consecutive ranks should have at least 1 male candidate and at most 2 male candidates. So clearly this ranking in the ranks 2, 3, these are 2 consecutive ranks, that there is no female candidate here. Therefore, this is not group fair according to these fairness constraints. So one way to achieve group fairness is to consider this given ranking to be a true ranking, and we re-rank the items such that the group fairness is satisfied. So for example, here it is possible to rearrange the items and achieve group fairness. So here, if we just want group fairness in blocks, then moving 5 to rank 4 suffices. Because, okay, so the candidate 3 need not be moved down to 4. The 1, 2, 3 remain in the same ranks. Only the 4 and 5 are rearranged. So this is a weaker notion. So there are more candidates that are in the true ranking. So clearly, some of the candidates in the true ranking are being pushed down the ranking. So as we saw earlier, the visibility of an item or the candidate depends on where they're being ranked. So the higher the rank, the lower the visibility. Therefore, Bob here has lost some visibility due to this re-ranking process we are doing to achieve group fairness. So to capture the worst case loss of an individual while re-ranking, we define what we call underranking in a group fair ranking. That is, a ranking satisfies gamma underranking if the rank of each item is at most gamma times its true rank. A true rank is a rank of the item in the true ranking. So Bob's true rank is 4, and after rearranging from for group fairness, his rank is 6. Therefore, his underranking is 6 divided by 4. And turns out this is the worst case. Nobody else has suffered more underranking than Bob. So clearly there is a trade-off between group fairness and underranking. So as the group fairness increases, the underranking also increases. However, the lower the underranking, the better for all the individuals involved in the ranking process. So the question we study is, what is the optimal trade-off between group fairness and underranking? Notice that high ranking utility does not imply low underranking. So therefore, any works that have studied group fairness versus ranking utility do not imply anything for group fairness versus underranking. So we first show a lower bound on underranking. So we also give a polynomial time algorithm, a very fast algorithm that proceeds in 2 steps. In a high level, in the first step from the true ranking, we construct an intermediate ranking of length more than the true ranking, where we move items down the ranking in the order they appear, and we create gaps, enough gaps, so that the fairness constraints can be satisfied later. So in the first step, the process we are doing fixes the underranking for the item. So after this step, no item will be moved further down the ranking. Therefore, this fixes underranking. After that, we move the items up carefully so that the group fairness constraints are also satisfied. So with this algorithm, we get an upper bound on the underranking, which is very close to the lower bound that we have proved, while achieving some approximate group fairness. And yeah, if we only want group fairness in blocks of size k, which is a weaker notion of group fairness, as we have seen earlier, we get optimal underranking and group fairness trade-off. So we also have run experiments. For example, we look at the German credit risk dataset, where the items are each assigned a Schufa score, based on which we get a score-based ranking. And in this score-based ranking, the adults of age strictly less than 25 are a protected group, according to some observations made earlier in the literature. And our algorithm achieves the best of both. We consider another data set called the Compass Resolution data set. Only our algorithm achieves the best of both representation and underranking. Running time, average wall clock running time of the algorithms also indicate that our algorithms runs much faster than our baselines. Yeah, so that's it. If you have any questions, please let me know. Thank you.